Our second pattern of chemical change are known as decomposition reactions. You know, everything that we just practiced in our combinations are going to come back to us in decompositions, but in the opposite order. A combination pattern was building a larger single product from building blocks. Our decomposition pattern is the exact opposite, taking that single reactant and breaking it down into simpler substances. So in our note packs, just where we left off after our last example of combination reactions, we'll pick up in our new lesson and talk about decompositions. We are going to state that a decomposition reaction is when a single reactant breaks down into simpler substances, and it is unique from any of the other patterns of chemical change because it indeed is the only pattern that has one and only one reactant. If we take a compound A, B, and we break it back down into its building blocks, compound A plus B, we've separated the building blocks, haven't we? A single reactant breaking down into the building blocks it came from. In a combination, we built it. In the decomposition, we break it back down. The opposite pattern of where we started. Just as the combinations had helpful hints, our decompositions will have helpful hints as well. And I'd like to go through those helpful hints one at a time and show examples, just as we did with our combinations. You'll notice that many of the decomp patterns are exactly the same but in the opposite direction as the combinations. In the combination, we talked about acids being built from nonmetal oxides. We'll look at our first helpful hint for the decomposition, the breaking down pattern. We're going to take some oxyacids. You remember what acids are? They start with an H, they end with an O, and they have some non-metal oxide. I'll just put it some generic letter. Some non-metal oxide in the center. When I recognize a oxyacid, I do so by seeing the element hydrogen and the oxygen at last. So for example, an oxyacid might be HNO3, nitric acid, H2SO4, sulfuric acid. Something along those lines are called oxyacids. And when we build them, we take a nonmetal oxide and place it into water. When we decompose them, we take out the water and we're left with the non-metal oxide. When an oxyacid starts with an H, has a non-metal, should we put X or maybe NM for non-metal oxide? This would be a generic formula for an acid, an oxyacid. What I want us to do is to subtract out the water and see what's left for the non-metal oxide. So I said a key word. I said subtract. Subtract a water from your original formula and just see what's left for the other product. I remember saying that the combination patterns were like addition problems. These are going to be like subtraction problems. Let's model that. Sulfuric acid. The polyatomic ion it came from was 8. Sulfate, a polyatomic ion, SO4, and we know it carries a -2 charge, sulfate. To make it an acid, its first name must be the hydrogen ion, who we know carries a +1. To make it electrically neutral, H2SO4. Sulfuric acid is called an oxyacid. And when oxyacids decompose, generally through heating, out comes a water molecule. I want us to subtract a water and see what's left, what's the remainder for the non-metal oxide. So I've got S something, O something, where those somethings are going to be subscripts. let's tally what we have. We have 2 H's already accounted for in the water, all set there. We have 1 S. I'll leave this subscript as a 1. And there's 4 oxygens. I've used 1 to make a water. How many are left? Well, if I started with 4 and I used 1, you got it. I have sulfur trioxide. The nonmetal oxide that forms is found by a little subtraction problem. Find what's the remainder not yet used when I subtracted the water. When oxyacids decompose, they make water and a nonmetal oxide. Nitric acid is heated. Nitric acid is an oxyacid. It comes from the polyatomic ion called nitrate. Acids start with an H, and we need to find the polyatomic ion called nitrate. NO3 is a -1. So here we have H plus 1, NO3 -1, nitric acid. When an oxyacid decomposes, I want us to consider a subtraction problem. Remove the water. I know water must come out. But now what do you notice here? I just want to play a little chemical detective. Do you notice how we have 2 hydrogens? We have to have 2 hydrogens to make a water. But over on the left side, this particular oxyacid only has 1 hydrogen in the formula. It's written that way because we know compounds are electrically neutral. I bet you can help me predict that the coefficient here in front of the oxyacid has to be a 2 to provide me with enough hydrogen to make a water molecule. 2 H's necessary for water tells me I better put a 2 out front here to get me the correct number of H's. Now what's left? Here comes the subtraction part. Subtract and see what's left. That's supposed to be a little s. Subtract. So the nonmetal oxide, I know it's going to be N something, O something. The nonmetal oxide. And those subscripts will be found by subtracting. Well, how many N's are over here? Notice this coefficient. 2 distributes through there. There's a total of 2 nitrogens. Subscript 2. Notice there's a total of 6 oxygens. 2 times 3 gives me 6 oxygens. But we've already used 1 of those 6 to make the water. How many are left? You got it. There's 5. The nonmetal oxide is N2O5, dinitrogen pentaoxide. When I showed this example in the previous lesson in the combination, we built this molecule and we started with, you remember this? H2N2O6. I said, wait a minute, we got to reduce that down 1 to 1 to 3, but we kept it balanced with a 2 out front. Same equation, opposite direction. Let's go on and look at number 2. Some metallic hydroxides, which we know as bases, when they're heated, will break apart, decompose, to break down into simpler pieces to form the metal oxide and water. And that water should be up here. So we've learned this in the combination pattern, didn't we? A metal hydroxide is what we call a base. A metal hydroxide is a base, opposite of the acid family. And when it breaks down, it's going to give off the metal oxide, better balance the charges, and water. When a metal oxide and water. Opposite of helpful hint 4 for the combination patterns. I'm just reminding us that this has to consider crisscross when we're writing out the pattern. So let's model. We have a metallic hydroxide. Sodium is a metal. Na carries a +1 charge, a metal. So here we have sodium, Na. It's its +1 charge. Your base ion, hydroxide, OH, and it's a -1. So far the base, the metallic hydroxide, NaOH. It's going to give off the metal oxide. Remember to consider charge, Na2O, and water. When a base decomposes, it gives you a metallic oxide and water. And we'll balance this equation by placing a 2 on the left-hand side. What if we have a calcium hydroxide? Just to throw another example, remember here calcium in group 2A, now it's going to be a +2 charge, just to show a little different, a little different flavor from the first example. So here we'll have calcium hydroxide, there's our base, calcium hydroxide. So when I crisscross to equalize charge, we get CaOH taken twice. And we're going to heat that to force it to decompose. When a metallic hydroxide decomposes, and let's write that out, just repetition to make sure the pattern sticks. This is called a metallic hydroxide, OH -1. We're going to make a metal oxide and water. The reason I like to write these out, again, practice makes permanent. The metal, calcium. The nonmetal is oxide, based on charge to equalize, CaO. And of course water is H2O. A single reactant breaking down to simpler ingredients. CaO plus water are the products in this decomposition. And this one indeed worked out balanced. I like those. Let's go on. Helpful hint number 3 deals with the polyatomic ion called a carbonate. Carbonates are a polyatomic ion, CO3, carrying a -2 charge. Carbonate, ATE, polyatomic. When carbonates are heated, they form the metal oxide and carbon dioxide gas. This should be up here. Carbon dioxide. Your note pack is written better. Let's write that out in words. Here we're going to have some metallic carbonate. So let's write a metal carbonate. Carbonate, spell it with me, B-O-N-A-T-E, carbonate, is going to give a metal oxide and carbon dioxide. Let's show an example. We have copper carrying a +2. The Roman numeral is telling me it's a +2. Carbonate, that's our polyatomic ion that we're studying. When carbonates decompose, they have a very specialized pattern. Alrighty, here we have a metal carbonate called copper 2 carbonate. The metal here is copper. The metal and the last name is carbonate. And when it decomposes, it gives the metal oxide and carbon dioxide. And now that metal, we could just put the word copper. Copper carbonate is going to give copper 2 oxide, Cu carrying its +2, oxide carrying its -2. There's our metal oxide, and there's the bubbles. Carbon dioxide will come out as a gas. So here we have carbon dioxide as a gas being liberated from carbonates. When we heat up carbonic acid, for instance, in a can of soda pop, it starts to bubble. Those bubbles of carbonation are known as carbon dioxide bubbles. Carbonates bubble when they decompose to release carbon dioxide. Let's talk about a next polyatomic ion that has a very special pattern, so it gets a helpful hint. They're called chlorates. This is a polyatomic ion found on our chart. ClO3 carrying a -1 charge. Chlorate. When chlorates are heated, they give off the metal, oh dear, this is wrong. Please fix this with me. Cross this off. The metal chloride and oxygen gas. The metal chloride and oxygen gas. Chlorates give off chlorides. Okay, so now let's model that. Polyatomic ion, chlorate. So let's find what we're referring to. Potassium. See how that's a first family element, so it would be a +1 charge. Potassium. The polyatomic ion we're practicing in this helpful hint is called a chlorate, and it carries a -1 charge, so we are electrically balanced with a simple KClO3. This is what we refer to as a metal chlorate. When it's heated, it will decompose, and I'm going to just write this out to find the metal chloride. Alrighty, metal chloride and oxygen gas. Oxygen. The metal chloride, Cl -1, chloride. Chlorate, polyatomic ion. Chloride, a monoatomic ion. And of course here's molecular oxygen, O2. Chlorates let go of their oxygen. Alrighty, so that if they let go of their oxygen, it doesn't come out as O3. In nature, oxygen exists in a diatomic form. And so when we balance, we get a 2:2:3 ratio. Chlorates make chlorides and oxygen gas. Doing well, we're doing well. How about binary compounds? Binary, what does that term mean? Well, of course it just means two elements. This is like the pattern of chemical change we wrote earlier. When a binary compound breaks apart, there's not a lot of choice for it. It's simply going to break apart into the elements it's built from. A binary compound such as AB is going to separate into the two elements A and B. So if we consider an example, water. Water is a binary compound. It's built of two elements, H's and O's. And we know just based on charge, this molecular compound we call water is H2O. But when we separate it or zap it with electricity, that's my lightning bolt if you will, molecular hydrogen and molecular oxygen are released. The natural states of these elements are diatomic. So when we balance, we get a 2:2:1 ratio. Compound AB separates into the elements A and B, but I write them in their elemental form. If silver oxide, so I write my compound based on charge, Ag2O. This is a binary compound. Binary simply means it's built of two elements, Ag2O. So when they separate into their building blocks, we get the elemental form of silver and the elemental form of oxygen, which is the lucky 7 diatomic molecule. And once I get my skeleton set, we go back to balance. 2 O's on the right, 2 on the left, giving me 4 silvers here. A 2-4-1 coefficient ratio. Boy, we're really doing well predicting patterns of decompositions. I've shown you 5 patterns that will help us predict any possible decomposition. So using these helpful hints, let's talk through these examples. We'll just keep working together. Again, practice makes permanent. And talk about what helpful hint we're going to use as we predict how something breaks down into simpler pieces. So for instance, in our first one, I'm noticing an important word, carbonate. Carbonates. What helpful hint talked about carbonates? Was it number, I'm trying to hit here. Hydroxides, nope. Not number 2. How about this one? Number 3. Number 3, carbonates. Carbonates decompose to give me oxides and carbon dioxide. So when I consider this helpful hint, we're going to use helpful hint number 3. When calcium carbonate decomposes, we're going to get calcium oxide. Based on charge, we get Ca plus 2, O minus 2, and carbon dioxide gas. Does this come out balanced? When calcium carbonate decomposes, the metal oxide and carbon dioxide. I like these. These are balanced, so my skeleton already is balanced. Almost done. Let's try number 2. See this helpful hint? Chlorate. Chlorate. Let's go back and read helpful hint number 4. When metallic chlorates decompose, metal chlorides in oxygen gas form. Helpful hint number 4 is going to be my guide in predicting this decomposition reaction. When magnesium chlorate decomposes, we start with our balanced charges, so we get MgClO3 taken twice. There's the chlorate. Makes our metal chloride, here the ending change. Magnesium still a plus 2. Chloride carrying a negative, so crisscross with me, MgCl2. And the molecular oxygen here, O2. The elemental form of oxygen is diatomic. Now this one will need some coefficients. I noticed that first of all the oxygens are upsetting. There's 2 on the right, 6 on the left. So I'm going to just place a 3 in front of the molecular oxygen, and I think we've got it. 6 O's, check. 2 Cl's, check. And 1 magnesium, perfect. Good work. Let's try our next example. Hydroiodic. That's a funny word, isn't it? Hydroiodic. It's a binary acid. I know binary because I'm seeing this prefix hydro, so that means the original ending for this acid name was "ide." I want to find iodide. Let me just pull up my periodic table to show you what I mean here. Here's my periodic table. See this element iodine? I is going to be a -1, iodide. And so when I'm considering hydroiodic, it really is just the element iodine as written as a negative charge. Let me get back there. So here we have HI, hydroiodic acid. It's a binary compound, so it simply separates into the elements it's built from, hydrogen and iodine. You're hearing my dog bark in the background. 2 HIs. This is helpful hint number 5. Binary compounds separate into their elements. We have 2 more to go. Stay with me. We have magnesium hydroxide. This looks like a base, doesn't it? That base ion. Helpful hint number 2. MgOH taken twice. When a metal hydroxide breaks down, we make the metal oxide and water. So we can simply write the water part first if you'd like. And the metal oxide would be Mg. We know it's a +2. O is a -2. So think of the pattern here. We start with a hydroxide. I'm writing that word. You do as well. Hydroxide. And you end up with the metal oxide. Here the nomenclature difference. Hydroxide, polyatomic ion, means base, the opposite of an acid. Let's go of the water, leaving you a metal oxide. And this one, yay, worked out balanced. Friends, we have one more. We can do it. Sulfurous, here the OUS. Acid rules we learned in the nomenclature chapter. Ite was the polyatomic ion original ending. This is an oxy acid coming from the polyatomic ion sulfite. There we have it, H2SO3. Read with me, helpful hint number 1. When oxyacids decompose, they release water and the non-metal oxide. Think of it as a subtraction problem. I'm going to remove the water first, so notice this is an oxy acid. Write that under there so you recognize that to take a water out, and I want you to subtract to find the other product. We know it's going to be S something, O something, where those little somethings we call subscripts. The non-metal oxide. So how many S's do you count on the left? You're right, there's one of them. How many O's? Well, there's 3, but remember we used one already in the water, giving us the remainder of 2. We made sulfur dioxide, SO2. You've done really good work with this decomposition pattern. You're ready to try some on your own, giving yourself feedback with the solutions provided. Good work today.